Thank you. And thank you to the organizers for inviting me. It's really been fantastic to be in Rio. I've always wanted to come to Brazil. I took a year of Portuguese 20 years ago in college, which has meant that I've been able to say, good day, thank you to everybody I've come across. That's about it, but that's okay. But muito obrigado to everybody here at IMPA. It's been just a beautiful week. It'll be nice to get the talk out of the way so I can enjoy the rest of the conference. All right. So I'm going to start with a little number theory. We'll quickly get away from number theory, but first I want to define the Mahler measure. I'm going to talk about Mahler measure of polynomials of one variable. And so the definition is this right here. You can just think of it as being the geometric mean on the unit circle of a polynomial. This polynomial may have complex coefficients, or in the number theory case, arithmetically defined coefficients, say integer coefficients. But we're quickly going to get to the point where we lose the integerness altogether. Now, it's a relatively easy fact from complex analysis that if you factor your polynomial into roots and a leading coefficient as such, then the Mahler measure is essentially the product of the absolute value of the roots outside the unit circle. You also have to take into account the absolute value of the leading coefficient. Now, what we're going to do here is we're going to identify polynomials of degree n with their coefficient vectors. So really I want to think of this as being a function not on polynomials per se, but on a vector space where I just identify each vector with a polynomial. Well, we can define essentially what is more or less the unit ball of Mahler measure once I've restricted the degree to degree n. Here, k is just going to be either r or c, and I'm just going to look at things that have Mahler measure less than or equal to 1. Now, this is not literally a unit ball, because Mahler measure does not satisfy the triangle inequality, and so therefore this thing is not convex, but except for that, you can think of it morally as the unit ball. Now, it's kind of horribly well behaved. It is star-shaped with respect to the origin, but you'll notice a few things about it pretty immediately. One is, for instance, the polynomial x minus 1 to the n certainly is monic, and certainly all of its roots are on or inside the unit circle. This thing has a rather large 2 norm, though, when you look at the coefficient vector. Right? And so the part of this star body must get pretty far away from the origin. On the other hand, there are polynomials like x to the n minus 1. You can't ask for a much smaller 2 norm than that thing right there. And of course, all of the roots are on the unit circle again. And so this thing certainly has things that have small 2 norm as well. That should be kind of sensible. But then there are also polynomials, for instance, this one right here. I'm writing this in terms of degree 10, but you could always just multiply by your favorite monomial to make this whatever degree you want. And you would see that the 2 norm of this polynomial right here is relatively small, right? But this thing has a Mahler measure approximately 1.17. So it is not in this star body, right? And as a matter of fact, for irreducible integer polynomials, this is the irreducible integer polynomial with the smallest known Mahler measure today. There's a famous question of D.H. Lamer that asks if 1 is a limit point of Mahler measures when you restrict to polynomials with integer coefficients. It's a theorem of Kronecker that he certainly did not state this way. The Mahler measure of an integer polynomial equals 1 if and only if that polynomial is a product of cyclotomics, and perhaps you could throw a monomial in there as well without disturbing things. All right, so in some sense, Lamer's question is the question of, can you find polynomials that are arbitrarily close to being cyclotomic without being cyclotomic, if you think of the Mahler measure as the cyclotomicness of a polynomial. All right. At any rate, there are another question that one likes to do with these sorts of things, kind of like in Uri Schinkel's talk, is to talk about the number of polynomials which have bounded degree and bounded Mahler measure. So, or you can just think fixed degree. It's not going to change things very much. Let's fix the degree at n. Let's pick our favorite real number t, and let's talk about the number of integer polynomials with Mahler measure less than or equal to t and degree equal to n. Well, there are finitely many, but how many are there? And the answer, perhaps not surprisingly, is when t is large, well, okay, t to the n plus 1, and there's a constant in front, and the constant is the volume of this star body in Rn plus 1. And this is not surprising, and then the error term right there, which presumably has something to do with the surface area or whatnot. Okay, well, this observation would be useless if that number couldn't be computed, and so my advisor with one of his former students proved, this is slightly different language here, lambda is just going to be Lebesgue measure, or volume. This right here is the star body, and they proved that the volume of the star body is given by this rational number. This is a little bit surprising that the volume of such a thing is a rational number, and a rational number that has kind of this, a relatively simple form. I mean, yeah, it's a rational number, but it can be described relatively succinctly. One can kind of do the same thing if you just wanted to know the volume of the complex star body, and its calculation is slightly simpler. All right, so the question that I want to talk about is the following, and that is, well, we have this volume. What if we pick a polynomial uniformly from this volume? This is a compact set. We know what its volume is. Let's just pick a polynomial uniformly from there. What can we say about the roots of such a polynomial? Okay. Now, this may or may not be a motivation, but one could say that perhaps integer polynomials or some with bounded Mahler measure are typical in some sense, or would behave like a typical point in this volume. I'm not willing to say that, but if one needed a motivation for doing this, from number theory, one could, I guess, use this as a motivation. It turns out there are other reasons that maybe physicists will appreciate more. Okay, well, so here I've done this. Actually, I haven't quite done this. It's not clear what I've done here. This is a polynomial, the roots of a polynomial that's random to me, right? It's a little bit hard to sample from these star bodies because, as mentioned, they have points of extremely large 2 norm, right? But they kind of avoid lots of places as well. So it's not one of these things that you can just sample from a ball of radius, say, 2 to the n when n is large, and then discard a point if it's not in the volume. That you'll just never hit something. So what I did is I kind of started at the origin, and I just did a little random walk, making sure I stayed in the star body, and I stopped when I sensed my computer getting tired. So this is not a literal sampling, but it's a pretty good, I think, in terms of the sorts of phenomenon that we can expect. Of course, these polynomials are real, so their coefficients come in complex conjugate pairs. That symmetry is easy to see. Some of the roots could be real, right? They could be on the real axis, right? Like so. And these arrows just point directions where somewhere out there is a root. So there appear to be outliers from this. I don't remember what the degree is, nor do I really care. All right, so I want to talk about the kinds of problems, the kinds of questions that we might ask. And maybe, there we go. Okay, so here is a slightly different model, but this is one where I can kind of explain what's going on a little bit earlier, a little bit easier. So what these are the eigenvalues of a square matrix whose entries are real, independent, and just chosen to be standard normal random variables. This is sometimes called the real Ginebra ensemble. Right? And it satisfies something called the circular law, right? Which basically says that as long as the size of the matrix is large, then the eigenvalues of such a matrix with high probability tend to uniformly fill up the disk of radius. I think it's square root 2n. It might be square root n. But at any rate, this is called the circular law. And, I mean, of course, here we're still in a situation where the eigenvalues must either be real or complex conjugate pairs, but we see different sort of behavior. Right? But at any rate, I just want to use this picture to kind of motivate what we might be interested in. In particular, we're interested in what happens as n goes to infinity. Right? So one thing that we might do, oh, you can barely see that. That's very disappointing. There's a little disk that's light orange right here. We can look in a neighborhood, but I want to put myself on a scale where somehow I'm independent of n. So in other words, what I want to do is I want to, for whatever finite n we're looking at, put myself on a scale where there are, say, in this disk, expected number of roots will be 1. Okay? So, for instance, again, you can barely see the little disk, but here's the outline right here. Right? I just kind of eyeballed it. It's not clear that this is exactly the scale. But at any rate, we put ourselves on that scale, and then we let n go to infinity, and hope that there's some sort of limiting behavior that says, well, as long as n is suitably large, then you're going to see this sort of correlation or this sort of behavior with respect to other roots. Right? This allows us to talk about things uniformly for n and then send n off to infinity. Now, of course, there are other regimes. So, for instance, I could look around a point on the real axis, and I expect to see different behavior because I have to have complex conjugate pairs in a neighborhood of the real axis, right? If I'm somewhere in the upper half plane and I'm on this scale, eventually my disk will not intersect the real axis and I won't be able to detect that the real axis is there. Right? But so you can zoom in on the real axis. Now, there are other places to look. For instance, I can be off the real axis, but I can be near the edge of this circle. Right? And here, somehow, I expect to see more eigenvalues in one direction than the other. Right? One should be able to detect this. And then, of course, there's a fourth regime, which is going to be given by what happens when you're at the edge of the spectrum, but you're real. Right? So these are the sorts of questions I would like to answer, but I would like to answer them not for this ensemble, which I've answered for this ensemble previously. This is kind of where I cut my teeth in random matrix theory. But for this Mahler ensemble of random polynomials. Okay. All right, now there are other kinds of statistics that arise, and you might have seen this. So this is a situation where we're looking at, say, random matrices that are Hermitian, and so all of the eigenvalues are going to be real. Now what this picture is trying to demonstrate, this right here would somehow represent some sort of histogram of where the real eigenvalues lie. Right? So this is a different picture than I just shown you. This is just counting more or less, or giving you a picture that would look like what the histogram would look like. Right? And here, you can zoom in again on the scale where you expect to see one eigenvalue per unit. Right? And if you do this kind of in the so-called bulk, that is some place where you expect to see eigenvalues on both sides of you, and you normalize things appropriately, you get something called the sign kernel. Right? This is the thing that arises in, for instance, Montgomery's pair correlation conjecture. There are other places to look. If you look at the edge of the spectrum here, you get something called the Airy kernel. And I've drawn this kind of suggestively to say that if you're in a situation where the eigenvalues, suppose, have to be real and positive, then that introduces a different kind of edge here at the origin, right, where you can't go negative, and so something different has to happen. Here, you might have high probability of being to one side or the other of some point, but there's no real thing that keeps you from maybe floating out here. Right? But here, there's a hard edge, and here you get a Bessel kernel. Right? The sign kernel is the one that comes up in terms of L functions, mostly because we expect L functions, at least typical ones, to have infinitely many zeros, and so you don't really have an edge of the spectrum per se. There's another kind that can arise, and this is if you have a situation like this, where you kind of have two bulks that kind of come together and smush together, you get what's called the Prc kernel. At any rate, the reason I'm bringing this up is that there are many details about random matrix theory that say, well, okay, let me say it like this. There's two kinds of random matrix theorists, three if you count people who do applications. I don't. So there's two kinds of random matrix theorists. One kind works for very specific models of random matrices, deriving the kinds of kernels, or deriving the quantities which control the local statistics of eigenvalues. Right? So this. Now, there's another kind where they say, okay, I'm not going to analyze a particular model, but I want to show that I have a large class of ensembles, a large way of picking the randomness, and I know that in the limit, if I have any two models from this big set of models, that my statistics are going to be the same in the limit. Right? And then you put these together, and you hope that in this large class, that there's one of these so-called solvable models, where the statistics can be described completely explicitly in the limit. And so you can put that together with the other piece of information and say, aha, I have one that I can describe. I know everything in this universality class converges to the same sort of statistics in the limit, and therefore I can describe the limit of all of these. Right? So I'm more the kind that says, okay, let's look for a solvable model, and let's try to describe these statistics with the hope that you're describing a large universality class, that you're really describing statistics that are going to arise in lots of other contexts. The miracle of universality is kind of like the miracle of the central limit theorem. Once you understand the central limit theorem, it's not miraculous at all. Right? And the same thing is true with universality. I mean, there is much made of this, accidental discovery by Montgomery and Dyson that the eigenvalue statistics, hypothetically, of the Riemann zeta function must behave like the eigenvalue statistics of the Gaussian unitary ensemble. But, I mean, let's face it, if they hadn't bumped into each other, somebody would have figured that out within a couple years. Right? This is not such an exotic thing, especially in the sense that the number of universality classes, the number of things that describe these things right here, there's really not a whole lot around. Right? There's not a whole lot of different kinds of statistics that we know about that exist in the limit. Okay. At any rate, I don't want to denigrate neither Montgomery nor Dyson. They're both very smart people. I'm just saying that discussion was not a miracle. Okay. Yeah, okay. That's true. That's true. All right. Now, I want to generalize things a little bit. We started with the Mahler measure. But I want to axiomatize things just a tiny bit. And so I want to suppose that I have a function on polynomials. Again, at some point, I might decide to replace polynomials with their vectors. But my rules are, I want this function to be continuous when I do this identification with polynomials with the coefficient vectors. Okay, so I want something which is continuous. I want some sort of homogeneity condition. So basically, I just want the existence of a real number so that if I take a constant times a polynomial, that this function right here is going to scale basically in that constant, right, to some power. It turns out that that's useful. I want there to be some form of multiplicativity. Now, I have to say that I guess this right here is a little bit in violation of this thing right here. Oh, but I put degree f and g greater than 0. Okay, so I'm not self-contradictory. Okay, I want it to be multiplicative. The Mahler measure is all of these things, by the way. And for some reason, I put this in red. I'm not sure why. I cribbed it from a previous talk. But the red thing says, I want this function to equal 0 only for the polynomial that's identically 0. Okay. Now, the Mahler measure, this is just the same definition from before, but it satisfies all of these things. Here, L equals 1. Okay. So it satisfies these properties. Now, I want to be able to discuss the roots of a random thing, and so I have to somehow figure out what the roots are. Well, I can identify the roots with this space right here. I actually have to be a little bit careful. I probably should put, say, the upper half plane here, because if you know it has a root in the upper half plane, you automatically know what's happening in the lower half plane. But at any rate, morally speaking, the set of roots is given by, well, RL cross CM, where L is the number of real roots, M is the number of complex conjugate pairs, and I have to take a union over all L and M such that I have the appropriate number of roots. Okay, you might complain and say, hey, wait a minute, I could have double roots and things could go awry, but having a double root is a set of measure 0, and so as a probabilist, who cares? All right. one can compute the conditional density on roots given L. So if you say, okay, I'm going to demand that it has L roots, one can actually write down the Jacobian of the change of variables from RL cross CM into Rn plus 1, the coefficient space. Right? So the coefficients are given in the elementary symmetric functions, in the roots, right? And you can actually just sit down and compute the Jacobian. It's a little bit tricky, but it's not so tricky. And what you find when you do this is, let's see, hopefully I did this right. Yes, here are some details. Okay, you get, the Jacobian gives you the determinant of a Vandermonde matrix, maybe not surprising if you're any sort of random matrix theorist, in the variables which are exactly the roots. So all the alphas, those are the real roots. The betas and the beta bars are the complex roots, and so you make a big Vandermonde out of this thing, and this term arises. Now remember, the molar measure is multiplicative, and what that means is, well, if I have a polynomial, I can replace its coefficients. It's easy to write the molar measure in terms of the roots, and this max 1 absolute alpha and max 1 absolute beta appears. Okay, there's this parameter s, but I'm going to, when s equals n plus 1, the conditional density on roots, where you're conditioning on the number of real roots, is given, has this structure right here. Okay. Now, it's convenient to generalize things in an appropriate way, and so if I call this, let's call this the L homogeneous molar measure, I'm just changing the definition slightly, right? Then I can see that I have, this right here is the complex case. Let's see, did I do the real case? Yes, so in the real case, I have almost the same structure right here for this joint density, this conditional joint density. The only thing that changes is this constant right here. S is no longer n plus 1, it's n plus 1 over L. So it just gives us an interpretation of that. All right, I kind of want to go through this a little bit faster. Here's one way to make a multiplicative height. If you have a measure, nu, supported on the complex plane, you can form what's called the logarithmic potential. Well, this is the exponentiated logarithmic potential as such. Basically, all you do is you integrate log of z minus another variable with respect to that measure. Right? That right there is the logarithmic potential. And then I'm going to exponentiate things. Okay, that should be essentially trivial. And then you can generalize molar measure by essentially taking a polynomial and now exponentiating the integral of the log of the absolute value of that polynomial with respect to that measure right there. If you recall from the very first definition, if that measure is a uniform measure on the unit circle, then this exactly is the molar measure. Right? So this gives you a nice generalization. Okay, well, one can even go a little bit further, and this turns out to be a useful thing to do sometimes. If you're given a compact set, you can define the capacity of the set to be what happens essentially when you take that logarithmic potential, and that's a function of alpha. Let's ignore the exponent right here, and let's just integrate that with respect to the other variable. Right? This is called the capacity. And it turns out that assuming k is sufficiently nice, okay, there are some stupid sets out there that aren't nice, but they all have Lebesgue measure 0 essentially. So as long as your set is sufficiently nice, then there is a unique probability measure supported on k so that this quantity right here is maximized over all possible probability measures. Right? And that's called the equilibrium measure. Okay. So for such k, we can define a multiplicative height by setting phi sub k to equal phi sub nu of k. Right? And if everything is nice and you haven't done picked a set that was too terrible, then you're going to find that this thing, well, that you get a multiplicative height out. The continuity condition for multiplicative heights is maybe the hardest one to deal with. So you just need a little bit of regularity. Well, at any rate, if k has capacity 1 and this potential is continuous, then you get a multiplicative height. And as before, we have this kind of factoring thing. So you still get the absolute value of the leading coefficient. And then instead of having the max 1 absolute alpha term, instead you're going to have kind of this exponentiated potential show up right there. And this thing right here, this sort of height right here, is going to detect when a polynomial has all of its roots in k? Well, okay, if the capacity equals 1, otherwise you can normalize things. And so you can kind of make this so that it detects when all of the roots of a monic polynomial are in your set k. So in some sense, you can think of this as being, well, for the Mahler measure, if you think of it as a measure of cyclotomicness, right? It's a measure of when all of the roots are in the unit circle, in or on the unit circle. This is kind of the same thing, just replacing the unit circle with some other set. Now, okay, at any rate, the Mahler measure is equal to this thing when the set K is the disk. There is a little bit of arithmetic structure here. So for instance, what I can do, if I can extend my definition of Mahler measure to Laurent polynomials. I know that the Mahler measure of the monomial x equals 1. And so I can just define the Mahler measure of the monomial x inverse, or I can start with the original integral definition. If I define x inverse to have Mahler measure equal to 1 as well, right, then I've allowed myself to multiply by any monomial with a positive or negative power. And so I can talk about this on Laurent polynomials. Right. So if I'm given a particular Laurent polynomial capital F, pick your favorite one, I can compose that with my little polynomial. Think of this as kind of the thing that could possibly be changing. Capital F is fixed. And so I can form this Laurent polynomial, and then I can take its Mahler measure. Right. So for instance, kind of ignore that stuff. Okay, if you do the situation where you're actually looking at x plus x inverse, right, then polynomials that land in this algebra of Laurent polynomials, so polynomials of this form right here, are exactly what are called reciprocal polynomials. Their coefficients read the same forwards and backwards. They have special structure right here. And so one can define, if you look at the equilibrium potential on -2, 2, form a multiplicative height from that. That's going to give you, that object right there is going to tell you about the Mahler measure on reciprocal polynomials. So this is actually kind of important. Reciprocal polynomials do have a special place in the arithmetic story of Mahler measure. And here, essentially, if you look at this map right here, this map x plus 1 over x takes the complement of the disk to the complement of this compact set -2, 2. Okay, so this is a way of constructing many different things, many different multiplicative heights, i.e. a large universality class for some of the answers that I'm going to give you later. Okay. I promised some electrostatics, so let's do that. Now, let's suppose that we are dealing with particles. These particles are going to be restricted to the plane. Okay. And instead of having kind of the usual inverse square interaction, they're going to have a logarithmic interaction. Right? So basically, we want these particles to repel, z and z prime. So how much do z and z prime hate each other? They hate each other proportional to the log of the distance between them. Okay? And so if I look at the potential energy of a bunch of particles, so capital N of them, right, this is essentially going to be the sum of all of the hatred between all of the particles. Right? Okay, well, if all of these particles absolutely hate each other, right, and they also at the same time want to minimize their energy, then this is done by all of them running off to infinity. Right? I want to get away from everybody. This is not so interesting. So what we need to do is put some other thing in the picture that all of the particles really like. Right? So what I'm going to do is put a charged region, say the disk. Okay. I'm going to put the charged region. What I'm going to do is fill it up with some charge of the opposite sign from the particles. Right? And then I'm going to let that thing sit at equilibrium. So let it kind of minimize its own internal energy. And then I'm going to throw in all these particles. Right? And then the energy of the whole system is basically going to be, well, so here Q is the charge. This turns out to be the equilibrium potential, how much they love the unit disk. Right? And then the energy is basically going to be, well, the sum of how much these particles like the unit disk minus their hatred of each other. Okay? Well, okay, again, if they don't love the disk enough, right, if this charge on the disk is not high enough, then they're still all going to run off to infinity. That's still going to be the minimizing configuration. So I have to just make sure that there's enough love, that love beats hate. Right? All right. Okay, then a little bit of physics. One can run through this. Then you can ask the question, okay, well, if I'm in this situation, then what is going to be the relative density of states? Okay, well, so here what I'm going to do is I'm going to take this system and put it in contact with a heat reservoir. And so there's some temperature, capital T, K is Boltzmann's constant, that makes this thing essentially a dimensionless object. And what one would expect to happen is if there was no temperature, if everything was super cold, then these things would just go to their equilibrium configuration in this field, and that would be the end of the story. Right, but since we have a little bit of temperature, right, then we can have like thermal fluctuations, and I can ask, well, what is the probability of seeing my system in a particular state? And the state is completely indexed by essentially just the locations of these z's right here. And it turns out, this is Boltzmann's factor, that for reasons, it's a fun little exercise in steepest descent. It's not too hard to show that this probability is proportional to basically the exponential of minus beta times their potential energy. In other words, it should not. It should not. It should be, that should kill it. Yes. Of course it doesn't. Okay. Right. Now, we can also have kind of situations. This is a little bit artificial, but I want to connect this back to my earlier ensemble. So I can imagine that the particles either have to be stuck on a line, or if I have one in the upper half plane, it has a little friend in the lower half plane, a complex conjugate pair. It's artificial, but it's not the most artificial thing anybody has done in physics, so it's okay. Right? And it turns out that what you get is that in this model right here, that if you condition on the number of real particles, right, you get the same joint density. Right? So if I'm conditioning on L here, I'm saying there's going to be L real particles. Right? Okay, well, there is this normalizing factor right here. In other words, I want to be able to talk about the probability of finding my system in a particular state. Right? And so I have to basically divide by some number to make sure that the total probability equals 1. And that number is going to be, well, it's going to be a sum of other numbers. Right? And these numbers are going to be formed by essentially integrating this function right here over all possible configurations where I have exactly L real particles. Okay? And here, the fact that I have not used the upper half plane, right, this is kind of mediated by this 2 to the m right here, in case you were worried. I saw some worried people out there. Okay. So the partition function is then this rather ugly sum. Okay. Well, it turns out that when beta equals 1, okay, so that's the temperature right there, and the charge that I put on the disk equals n plus 1. That's just 1 bigger than the number of particles. Right? That this partition function right here, this thing that makes what I'm talking about a probability measure, is exactly equal to the volume of the star body for Mahler measure. Right? So here's the connection between physics. Now, okay, I'm going to do, this is just kind of a little bit of notation. Given a function, I'm going to, if anytime I put a little hat on my function, I'm basically just going to be multiplying that time max 1 absolute z to the minus s. Okay, this is just kind of a normalization. It just makes the formulas look nicer. Okay. And I have to define an operator. This is annoying. I'm going to try to get over this as soon as possible. Morally speaking, if the point is complex, this is basically complex conjugation. Okay, there's either a plus or minus I out front, but you should just think of epsilon as being complex conjugation. This looks even worse, but morally speaking, what you should think about here is this operator right here is anti-differentiation. It really is just anti-differentiation if you were to write that out, as long as your function decays fast enough at anti-differentiation. now what we have to do is we have to define a skew-symmetric bilinear form. Woo! Okay, and we do this as follows. What I'm going to do, if I have two functions, f and g, I'm going to make their little hats. Right? So basically, I'm just multiplying by that max, that sort of term right there. And I'm going to form f epsilon g minus g epsilon f. Right? And I'm going to integrate this with respect to a kind of a weird measure. It's a measure that has a part which is absolutely continuous with respect to Lebesgue measure on C, that's mu c, and has a part which is absolutely continuous with respect to Lebesgue measure on R. Right? Not the sort of typical complex integral that one does. One can do it, but okay. And then there's a theorem that says that the partition function, this ugly thing right here, turns out what I can do is I can pick my favorite family of polynomials. Okay, they have to have the right degree consideration, so degree 0, degree 1, et cetera, et cetera. Okay. I can form what is essentially a Gram matrix, so I can form all inner products of these polynomials with respect to this all inner products of these families of polynomials. This forms an antisymmetric matrix, right? Because I have this skew bilinear form. And it turns out that there is an important invariant of antisymmetric matrices called the Pfaffian. I'll tell you the very worst way that you should think about Pfaffians. This is the worst way. It's the easiest to describe, but it doesn't help anything ever. It's the square root of the determinant of the matrix. Never use that fact. There's a better way of thinking about it. And it's as follows. To every antisymmetric matrix, you can identify an antisymmetric matrix with a 2 form. So let's do this. Suppose I have A equals alpha j k. Of course, if I swap j and k, I want to get a negative sign out. And then I can make a 2 form. Let's call it omega sub A. And this is just going to be the sum, j less than k, of alpha j k times ej wedge ek, where say this is just e1 through e2n, you have to be even in order for this to work, is your favorite basis for a vector space. Right? So I've made a 2 form. Right? So this thing is in wedge 2 span R of this basis right here. Right? Fine. Okay. If I look at wedge A to the m, so I'm basically going to take that form and wedge it to itself m times. I'm going to divide by m factorial just for fun, because I can. Right? It turns out that this thing right here must be some constant times the volume form. So this thing right here is a constant times the form, e1, wedge e2, wedge e2m. And that constant right there is exactly equal to the Pfaffian of the matrix. Takes longer to describe, but that is the correct way of thinking about a Pfaffian. The square root of the determinant, that's terrible. Okay, at any rate, but it's true. All right. Well, okay, I have this inner product. It's not literally inner product because it's skew. But I can ask, is there something akin to orthogonal polynomials? Right? Well, the answer is there aren't literally orthogonal polynomials, because no matter what polynomials I make, once I construct the Gram matrix, it's going to be antisymmetric. In other words, I cannot make a diagonal matrix. But I can make the next best thing. Okay? And this is basically going to demand that basically all of the entries that are indexed by both even numbers, I want that inner product to equal 0. Or if they're both indexed by odds, I want that to equal 0. And then I basically want there to be some relationship between, say, the 0 and first of these polynomials. That inner product I want to be non-zero, right? And then the 0, 1, second and third polynomials, I want that inner product to be non-zero. Right, second, third, fourth, and fifth, right? So on and so forth, and all other entries are 0. This is kind of the analog of what a diagonal antisymmetric matrix might look like. Okay? Well, it turns out, so I just wanted to be diagonal. You can also make skew orthonormal polynomials, and one can go back and forth just by fiddling with the leading coefficient. Okay? At any rate, there's a very easy fact akin to the fact that the determinant of a diagonal matrix is the product of the entries on the diagonal. The Pfaffian of one of these sort of skew diagonal matrices is basically the product of the non-zero entries on the first superdiagonal. well, okay, maybe. At any rate, it's going to be the product of these normalizations. All right, so I can do this in this case. It turns out that my skew inner product is kind of this terrible thing. All right, well, you know, there's the thing that makes it skew when I integrate over the complex numbers. There's the thing that makes it skew when I integrate over the reals, whatever. And you can actually cook up, I'm giving you the skew orthonormal polynomials, but again, there's an easy relationship between them and skew polynomials. And I can actually cook up these polynomials. Now, the way I did this originally, oh, is Bruce around? I promised him some 2F1s. Are those 2F1s? Yeah, see? I delivered. There's a 1F1 coming too, if I can stop yammering. All right. Okay, now the way I did it. Oh. Okay. Okay, there's that. Okay, yeah. I wasn't expecting anybody to want to actually know what they are, but it's, the fact is they exist. That was kind of more what I was, right. Well, one thing that is interesting is all of the S dependence. It's a real inner product because, yeah, I want to, as long as your polynomials have real coefficients. Right. Actually, I think even with that is, no, I think they have to have real coefficients because this thing right here, yeah. Okay. You happy? Okay. Notice that all the S dependence is on the odd ones. Weird. Okay. At any rate, so the way I did this originally 100 years ago in my thesis is I just computed this for the monomials. I was like, oh, okay. You know, I don't know anything about orthogonal polynomials. I'm a grad student. So I'll just put in the monomials and see what happens. Right? And when you do that, what you see is that you get this relatively nice formula out. I should say that there's a miracle that's going on here, because if you just look at the real part of the inner product and the complex part of these inner products individually, they're both rather complicated. Right? In particular, it's when you add them together that you get something nice. Notice that both of these, for instance, have poles that potentially at half integers. Right? This is something miraculous happens, that this inner product all by itself wants to be paired with this one in order for that thing to come out nice. After all, except for some diagonal terms, 4 over j and s over k minus s, the Graham matrix for this thing right here is a Cauchy matrix, right? Like the second best kind of matrix there is after Vandermonde's. I guess identity matrix is the very best, but you know what I'm saying, okay? Right? Whereas these sorts of matrices are just tragedies. At any rate, okay, blah, 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 blah. I'm going to kind of go through this a little bit fast because I've already said all of this. Okay, so the one thing I do want to say is now we're going to get back to the question of, the question of what can we say about the statistics of the roots of polynomials chosen from this molar measure star body or from this physical system of particles. Almost surely the roots are converging, the empirical measure on roots is converging to the unit circle. So they kind of want to get close to the unit circle. And we saw that in the first picture that I drew of the zeros of such things. Okay, so how can we encapsulate information about the statistics of roots? This is what a probabilist does. Okay, so what I'm going to do is for a bunch of sets, okay, so for instance, I have a bunch of subsets of the real numbers. These are these pink intervals. And I have a bunch of subsets of the upper half plane. These are these light yellow disks right here. I can form, for each one of these sets, the number of roots in that set. That is an integer valued random variable. Right? Then, if I have more than one set, I can multiply all of these together, and I get a new integer valued random variable. And I can ask for its expectation. The expectation no longer has to be an integer, of course. Right? So, one thing, especially with random polynomials, the first question one might ask is how many real roots are there? Right? So it turns out that, okay, there's a parameter right here. There's my s. Right? And so the number of the expected number of real roots inside the disk is 1 over pi log n, right? Plus lower order term. The expected number outside is going to depend on this s. This kind of makes sense. What this s is doing is when s equals infinity, it's saying that all of the roots have to be inside the disk. When s equals n plus 1, that's kind of a very soft situation where roots are allowed to kind of maximally be outside. Right? So one can come up with expressions for the, basically, these sorts of things. And this is a popular thing to do following cats. Okay? But that's just one thing that one can do. It turns out that if you can find a function RLM such that the expectation of this random variable formed by multiplying counts of roots in all these sets, if I can find a function on R little l cross C little m, notice I have little l real, say, intervals, and little, that should be a lowercase m right there, balls, right? If I can find such a function such that when these sets are all disjoint, I didn't write that down, but when all these sets are disjoint, I integrate that function, I get that expectation, then that function is called the correlation function. Now, it turns out that when you only have one species of particles, that the correlation function is morally up to a constant, just the marginal density of particles. But as soon as you have more than one species, that is no longer true. So for people who like to go around conflating correlation functions with marginals, should be careful. Okay, at any rate, it turns out that there exists a 2 by 2 matrix such that this matrix has to have special properties so that when I form this sort of block matrix right here, that this block matrix has to be antisymmetric. So if it's antisymmetric, then I can possibly talk about its Pfaffian. Right? If I can find that there exists a matrix function like this, such that RLM, right, this correlation function is given as the Pfaffian of this matrix. And the nice thing is that this k right here, this matrix function, does depend on n, the number of particles, but it does not depend on little l and little m. The size of the matrix on the right-hand side does, but the matrix itself does not. All right. Okay, I don't want to tell you what this looks like, except to say that I'm going to give you some descriptions of this object. All of the entries can be determined from the 1, 1 entry of this matrix thing. And it's formed from, in this context, the skew orthonormal polynomials times, this is what we can call the weight. This is the part that comes from the Mahler measure. And what I want you to think of is think of this kind of like the reproducing kernel with respect to a normal inner product. This is a skew inner product, so this is kind of like the skew reproducing kernel. Right? Okay, so I'm ignore this other crap. It's just really a pain in the ass. Okay, when n is large, we expect the roots to accumulate nearly uniformly on the unit circle. Thus, if I look in a radius, a neighborhood of radius 1 over n around a particular point on the unit circle, I expect to see big O of 1 roots, depending on what that radius is. Right? Okay, so we set Bn to be that. And then we expect, in this context, okay, the expected number is going to be the integral of the first correlation function right there. And you can play some games. I'm just going to do some changes of variables right here. Right? This is just computing the Jacobian. The fact that I'm in the complex case gives me a 1 over n squared there. Notice I did that change of variables. If we were integrating over a subset of R, that would just be 1 over n. Fine. You can kind of reorganize things. And so what do I expect? I expect this thing to converge, as long as I'm looking near a point on the unit circle. Right? But of course, the first correlation function, this correlation function is given as a Pfaffian of a certain matrix. This matrix looks like this. Okay, don't worry too much about it. If you want, you can focus on dn, because I told you what that was. Right? And so now, what I have is I expect this quantity right here, which is exactly that quantity right there. I expect this thing to converge, or at least, I mean, I'm going to integrate this thing over this small set, so I expect this to converge. Much like determinants, you can use multilinearity, and so I can move that term in. And so really what I expect is each one of these entries to converge. Okay. And I'm going to call that, at the point that I'm looking, I'm zoomed in around this point, I'm going to call that, well, k sub, what is that, a zeta? Maybe that's a poor choice in this crowd, of uv. Okay. Of course, I can do this at a real point too. When I look around a real point, then one has to be a little bit careful because the Jacobian could be a 1 over n instead of a 1 over n squared, and so you kind of move things in a different way. Right, I want to get to the punchline. Okay, it turns out that there's an invariance. It doesn't matter where you're looking on the unit circle. So if you're at a complex point, the answer is going to change relative to the direction towards the interior of the circle, but that's it. That's a minor kind of universality. All right, blah, 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 blah. I'm going to ignore this stuff. This is the complex case. I'm talking about Pfaffians. Okay, I'm going to just show you some pictures. Okay, so for instance, one of the first things you can ask is, what is the radial density? If I'm looking in a neighborhood, scaling like 1 over n, of a point away from the real axis, right, what is my radial density? I know if I'm at 0, that corresponds to being on the unit circle, but generically I'm allowed to be in the complex plane. Right? So I kind of have this sort of decay. And L right here is basically n over s. Remember, s has to be bigger than n. Right? When that equals 0, that means I'm not allowed outside the circle, and so the radial density has to die. Right? Otherwise, it turns out I get symmetry when L equals 1 for reasons I don't understand. But at any rate, this is encapsulating basically the local density as I get near a point on the unit circle. Okay. This is the 2-point function. So now I can ask, this is radial pair correlation. If I'm standing here at a point on the unit circle, what is the probability of me having a point in a neighborhood of A radially out from the circle and another eigenvalue or root, right, at some point B radial outside? Right? Now it turns out these particles, they still hate each other. Right? So most likely the way this is going to happen is one's going to be inside and one's going to be outside. But they both want to be on the unit circle, but not simultaneously. So if you look at this graph, you can see that. I only have a few minutes left, so I'm not going to let you look at it too long. It's pretty, though, isn't it? Tangential pair correlation. Okay, so this is kind of like sine kernel nonsense, right? Except here, so the points want to be on the unit circle. Okay, they want to be on the unit circle, but they don't have to be. What that means is it's not just a matter of pair correlation between the angles of the roots, right? They hate each other proportional to the distance between them, not proportional to the arc length of the circle between them, right? So you kind of get some sine kernel-like behavior, right? But you don't literally get sine kernel behavior because they can stray away from the unit circle, right? So just to give you a comparison, again, we have various things depending on that scaled parameter. Right? This is the Mahler measure case right here. This is the case where all of the roots are restricted to be inside the unit circle. So you kind of get slightly different things. On this scale, the sine kernel looks like this. Right? So these kind of tangential pair correlations are much softer, but basically it's because roots are allowed to stray into the complex plane to get away from each other. Right? You have another degree of freedom. Okay, now let's talk about the scaled kernel at the... You can also talk about the real part. Here, life is complicated because you can still have real points in the neighborhood of 1. You can have complex points in the neighborhood of 1. They all hate each other. They all want to be near the unit circle, but they want to be away from the real axis because they hate their complex conjugate pair. I know that seems weird, but it's like evil twin, good twin, right? And so there's all sorts of interesting behavior that happens here that doesn't happen in other ensembles, even Ginebra's ensemble. What a nightmare. Okay, I'm just going to tell you what dn is. Right? That's essentially the reproducing part. And I have to do this because I promised Bruce a 1F1. So, okay, it turns out if you define m of u to be this 1F1 right here, then you can form this kind of skew reproducing kernel in the following manner. Now, I don't really know what to make of this, except that it makes it nice to write the equation on one page, right? But that's mostly because you've hidden a lot of stuff into the nastiness of a 1F1, or the beauty of a 1F1 if you like these sorts of things, right? But you essentially are forming an antiderivative of this strange sort of m prime m kernel, right? I don't know what to make of this except that I can draw pictures. So for instance, if you look at the local complex density towards 1, what do I see? So 1 is right there in the middle of the picture. I'm looking at the density of complex roots near there. Notice the density is kind of low near 1, and that's because complex conjugates hate each other. Good twin, bad twin, right? But once I'm sufficiently far away from there, right, the farther away I am from the real axis, the farther away my evil twin is. Right? And so then I do want to be on the unit circle, right, which is this kind of rise right here. And there is kind of a connection between what's happening here. This is the case when I'm not allowed to be outside the unit circle at all. And I just want to connect this with the radial density. In this picture, if you look far enough away from the real axis, right, then I expect to see more or less the same radial density. I should basically, as I get farther and farther away from my evil twin, right, my evil twin has less and less effect over me. And so I basically should see the radial density in the limit as I get farther away. All right, and you do see that. I mean, you can see that. All right, the last thing I'm going to talk about, and I'm going to just, this is something that does not happen in normal random matrix ensembles. It turns out that the unscaled kernel also converges. What this means is that for any set away from the unit circle, so any Borel set, say, that does not intersect the unit circle, the expected number of eigenvalues in such a set is positive. In other words, there's always outliers. The expected number of outliers is positive. Okay, in the case where you force all the things to be in the unit circle, that's obviously not literally true, right? But there are always outliers here. This does not happen in normal random matrix theory. This does not happen in GOE. It does not happen in GSE. It doesn't happen in GUE. Right there, with probability 1, all eigenvalues go to the limiting density. Right? So here, again, I'm going to just zoom in around 1. You can still see how the complex conjugate pairs hate each other. As I get farther away from the unit circle, the expected number does go down. Right? But you can still see the hatred of the complex conjugate pairs. All right, hopefully I've given you an idea of the sorts of statistics that you can capture in this model. Right? There's more to be said. There is universality. There is a universality class. These kernels are new as far as I know, but my time is up.
Are there any questions for